All right. Hello, everyone. Welcome to Measure Twice, Tape Out Once inside AVCC's TR008, Guidelines for Pre-Silicon Benchmarking. I'm going to hand it over to the key author, Nicolai Behmann of Siemens, to start the discussion.
Thanks a lot, Mackenzie. This webinar is about reviewing the latest AVCC technical report we just published. You may have seen the announcements online and so on. It's the 8th technical report which we published. It's titled Guidelines on Pre-Silicon Benchmarking. And the purpose of today's webinar is to give you a brief overview of what kind of content you can find in the document. And also at the end of the webinar to give you a chance, if you even have reviewed the document or have questions during this presentation, then I'm happy to answer those at the end of this webinar. Anything we have to respect was, I think you can put the questions into the respective function of the Teams webinar. So please feel free to put questions there. I don't know if I'm able to see somebody raising the hand or something throughout the meeting, but definitely we will catch up later on. All right, that's all on the practicalities. Now let's get started with an overview of the guidelines on pre-silicon benchmarking. Just a few lines to myself. My name is Nicolai Behmann. I'm working for Siemens EDA based out of Germany. Solutions architect in the Pay 360 solution, where we are engaging with automotive customers. And a big topic we're addressing in this solution is pre-silicon benchmarking. And we will shortly see an introduction of why we believe putting out these guidelines can reduce efforts on OEM side, on IP company side, and on our side, and help getting performance estimations or performance verification before actual silicon is taped out. Of course, this technical report wouldn't have been possible with all the valuable contributions. There is a much longer list depicted in the paper, but I definitely wanted to highlight the main contributors. So this paper is, or the technical report is co-created between us as from Siemens EDA, ARM as an IP company, Cadence as another EDA vendor, Bosch representing here tier 1s and tier 2s. So we have a quite good mixture from the value chain of automotive to put all these different perspectives into the document. This is the table of contents you can find when downloading the PDF of the technical report. It's less than 30 pages. It's structured as depicted here. So we first have an introduction highlighting the motivation for such technical report and pre-silicon benchmarking in automotive in general. We will then introduce what a benchmark actually means, and we will shortly see that it has mainly 3 elements, which is also exactly the 3 following chapters. There is first the stimulus needed for a benchmark, so we will review those. Then we need a design under test, which we want to benchmark. That's the DUT section with different environment definitions and exemplary configurations for an NPU IP benchmarking use case and freedom from interference analysis. And lastly, we want to measure some KPIs from this. So we will also review different KPIs. The last chapters of the technical report are then future directions, discussion on what is coming next in automotive pre-silicon benchmarking specifically. And we think very valuable might be the last chapter 8 appendix with an RFI report template, which can guide the execution of RFIs for pre-silicon benchmarking between OEMs in tier 1s and tier 2s or IP companies. So let's get started with the introduction of why we wrote guidelines on pre-silicon benchmarking. The purpose is we want to ensure accurate, comparable benchmarking before physical silicon exists. Before I joined Siemens EDA, I worked at Volkswagen. I was doing pre-silicon benchmarking there, and this was mainly done by requesting performance numbers from different IP companies or SoC vendors. But we quickly figured out that if you get results, you cannot compare them apples to apples. There is always some tuning, some ambiguity which is used to have not matching results. Somebody may report results for a different tech node. Somebody may call memory inside his area or outside his area. Sometimes latency is assuming an idealized interrupt controller from the CPU. So there's always something which can lead to differences between the results that you get. And sometimes even some OEMs or tier ones are just starting the pre-silicon benchmarking exercise, and they don't even know exactly what to specify and ask for. So this guideline should help to get accurate comparable benchmarks. It focuses on the typical metrics we are comparing when exercising IP or SoCs or silicon in general, which is PPA, performance, power, and area. And we will later on see all the different sub-KPIs within these categories, which may be relevant. It's about pre-silicon benchmarking. We just explicitly states this excludes completely everything around verification of RTL and so on. That's not the purpose or the content of this technical report. It focuses around performance. We need pre-silicon benchmarking, especially in automotive electronics, due to the tighter development cycles that we have, exploding complexity in workloads. So the compute power that needs to be delivered is increasing dramatically. And we see that we want to have confidence early on that the electronics which we source, for which we produce customized PCB, ECU, housing, software stack, and everything, we want to make sure that all our performance targets are actually matched and hit. So for this, we can use pre-silicon benchmarking. We see also that it's relevant for many customers to use their own custom workloads rather than using standard benchmarks. So whereas in the past, maybe companies were just asking for a dry stone number or spec-in core mark or some other KPIs, we can see that there is an increasing need, especially in the neural network market, for customer-specific workloads or domain-specific workloads. So even asking maybe for a ResNet KPI, which is maybe already an outdated neural network, can lead that you get some benchmarking numbers, but you cannot hit the same performance target with your own workload. So you may want to run your own workloads as an OEM, not your one, or whoever is requesting the benchmark. The key objectives is to cover competitive IP benchmarking or SoC benchmarking. So if we want to compare different NPUs, for example, with each other, which NPU to select for the next SoC and so on. Even if one specific NPU from one vendor is selected, there is usually a large degree of freedom for configuration, which can be core count, interconnect, width to memory, the memory partitioning, and many other aspects, which the pre-silicon benchmarking can also within one NPU can help in right sizing the optimal configuration to hit the performance target, but not waste area and thereby have a higher cost. This is also then applicable to the hardware software co-design part. So pre-silicon benchmarking can even be used if you do a shift left of your software development, that you have a performance model of your hardware and that you can tune your algorithms for the respective hardware. And also it should serve for system performance validation. So we may want to measure boot time, which is a relevant KPI, which we need to be tracked, or some camera to display latency when we start the car, or other use cases. All different kind of system KPIs shall be validatable also with these pre-silicon benchmarks. So the applicability of these guidelines is from single IPs, exemplarily listed CPU, GPU, NPU, but it could also be DSPs or whatever else, to full system on chip, or even system in package and system of systems. We see a big movement in the automotive industry to go into the direction of chiplets. I think it's still unclear when and how this will be realized first time, but we see many actors in the industry working actively on this. And also in this respect, pre-silicon benchmarking is very relevant for the targets we listed above, but also, for example, to have power thermal profiles for package co-design and other things. So there is even additional elements coming up, which we will discuss in our future directions chapter as well. So let's get started with what a pre-silicon benchmark, or benchmark in general, is. A benchmark consists of three major elements, and those are also depicted at the bottom of the slide in these three boxes. First, we need a stimulus. This is basically the input for the benchmark. Could be a workload, could be a test bench. We will go into more details. We need the design under test that reflects the system that is benchmarked. In the system of pre-silicon benchmarking, there is different implementations of DUTs possible, and we will review different implementation strategies and their purpose and their applicability, which implementation may be ideal. And there is KPIs at the end, which we want to extract, and those are used to quantify the metric of interest. In this context, it's usually PPA, which we will also review. Coming to stimulus, first focusing on this heavily stacked burger diagram of many, many different layers that we have drawn here. It basically shows exemplary software stack in a car today. At the very top, we have applications or software components from AutoSAR, which may communicate through some level of middleware. So this is all yellowish colored because this is typically the application layer of software, which we are talking about, which is running on some level of BSP, which includes an operating system, AutoSAR, full operating systems like Linux, Android, everything. Could be a hypervisor, even hosting multiple operating systems on a single device. We have bootloaders underneath, firmware elements which need to be loaded for the respective hardware, which we have then colored in blue at the bottom. That should depict basically everything which we have modeled, or which we have in hardware on our system on chip or system in package. Starting with the top row colored in blue, there is typically application cores, CPUs, real-time cores or MCUs for safety critical and security related purposes, as well as system management and all of those things. We have GPUs for graphics acceleration, but also for neural network workloads and general purpose acceleration. We typically have NPUs, and there could be any other kind of accelerator right next to that, like a DSP or something. An interconnect, which usually connects all these different elements together, could be a network or chip or something, and then all different kinds of peripherals at the bottom, Ethernet, PCIe, UCIe, camera interface, all the other low-speed peripherals to communicate with the actors and so on, display controllers, and of course, very important, memory, which typically in automotive is a LPDDR class memory, which we have on the PCB, which is used to load and read and write all the data for our software. Now you see two purple colored octagons on the slide depicted A and B. And this should exactly show two different ways of providing stimulus to a pre-silicon benchmark. The A we call in our paper instruction-based stimulus. Basically, this could be a benchmarking application, which is executing on an operating system. The whole stack does not necessarily need to be identical to the final card for different reasons, software readiness, or just being far too complex in the loading state or something. So maybe if we run a quite complex system with hypervisors, maybe we just have a bare metal operating system. So there can be some variance when executing the benchmark, but the benchmark itself, we would say, is an application which we somehow install or put on the device and execute there. Option B instead is some kind of a traffic generator. We refer to this as being a signal-based stimulus. So we can imagine that here really we have a connection to the interconnect. Maybe it's an AMBER interface like AXI, APB, CHI, whatever. We may have pre-recorded traffic of the stimulus that we need, say for a GPU or something else. And so the traffic generator basically would interact with the device directly without really executing a whole context of software on top of it. And there, of course, can be something in between A and B, where maybe the stimulus is kind of instruction-based, but it's not like running on a Linux operating system, but much, much lower level, like bare metal execution. All of that is also possible. But in general, these two categories we distinguish in our technical report. So first, I'd like to give an overview of different benchmarks which we have gathered. So this should help when you have to decide for a GPU for a specific IP to give you a start of looking which benchmarks exist there, for which you may have already comparison numbers available out there, and also see which elements these benchmarks exist, and maybe you want to select a subset, for example, of a specific benchmark. Kicking this off with the CPU benchmarks is maybe one of the most relevant IPs for all the general purpose compute and so on. There is many established benchmarks also coming from other domains, which can also be run in automotive. There is, for example, CoreMark, which is a very compute-bound benchmark to execute. SpecInt, also including memory-bound use cases. We always have to keep in mind SpecInt itself and CoreMark and many others. These are benchmarking suites, which basically have different benchmarks underneath, each of them generating a score and then being averaged or some other way of mixing those to a final score. So it could be, for example, that in SpecInt you would say the runtime of a GCC compiler may not, or GCC compiler run may not be a representative workload for an automotive CPU running in a car, would most likely not run any compilation in safety critical situations or in general. So this may be something, for example, to remove from the SpecInt, but there's other benchmarks in those suites as well, which may be very well applicable still, or may have a similar memory accessing pattern. So it can still be used to derive some kind of KPI from the DUT. Drystone maybe is the dinosaur of benchmarks here. Geekbench CPU, there we have single thread and multi-thread variants. There's a speedometer 3.0 benchmark, and Antutu, this is pretty newer, partially coming also from the mobile space, but also relevant in this context. On the GPU side, we have listed GFX bench as a rendering benchmark, and that we have perceived as most used in automotive benchmarking. 3D Mark for rendering. Geekbench, which can even use OpenCL and some compute elements. So it's not only graphics GPU benchmarks, which may be using resources like texture memories and other things, but also can be just a GPU benchmark here to just stress the compute performance of the shader cores or other elements. Then there is a base mark GPU benchmark, and also here yet again the dinosaur GL mark or GL mark 2 with a rendering benchmark, pretty long there already in the industry. On the DSP side, we in these guidelines focused on audio DSP benchmarks. So there's a whole suite. You may see that the font is kind of blue and underlined. This means that there is actually a link, and also in our technical report, which you can download freely without any firewall. You can just find the references to each of these benchmarks there and dive deeper. The audio DSP benchmarks actually include encoding and decoding algorithms, filtering, upsampling, noise canceling, and different other things. We have later on a use case example for an NPU benchmarking. So we definitely need machine learning inference benchmarks. And AVCC together with ML Commons has created already a initial release, and the 1.0 release will be out very soon of MLPerf Automotive. So this specifies a stimulus, which is basically different state-of-the-art neural networks executed on our design under test with load gen. And the nice thing is for neural networks or machine learning specifically, there could be all different kinds of optimizations, which could be an NPU IP specific number format, for example. There is FP4, everybody wants to reduce the word length used to compute. And this obviously has not only positive impact on the performance that you can achieve, but may also reduce your latency. So this is a full benchmark suite, which also encompasses a reference data set, which is used to get accuracy KPIs from the algorithmic perspective. And additionally, you can get the PPA measurements, which are focus of this technical report. Also, there is Geekbench AI, which you may execute. The working group members have seen different image processing benchmarks. OpenCV itself is not a benchmark really in the sense of the suites we have above really computing scores, but OpenCV ships with a whole bunch of different functions. And it's pretty simple to generate a workload which may use one of these functions, which also have different implementations and may already be hardware optimized to actually stress a GPU, a CPU, or so on with image processing workloads. And you see this is all domain-specific benchmarks. So we also list even ADAS workloads like OpenADKit or AutoWare, which comes with a whole set of different nodes that you can benchmark, or ADAS bench is a complete ADAS benchmark. And for IVI, we have recollected AWS FutureMark here, 3D Mark as a real IVI specific domain benchmark. I was already highlighting a few things earlier, but this should be a summary of how does a pre-silicon benchmark differ maybe from a benchmark that you would run on a physical silicon device. The main difference between a physical device and a pre-silicon device usually is the time you need to execute, the wall clock performance that you see. So even though a pre-silicon benchmark can be very accurate with the KPIs it delivers, you can basically put a 2 gigahertz device in a pre-silicon DUT, but the wall clock performance of this, depending on what kind of implementation you chose for your design under test, can be significantly slower. So we are talking in orders of multiple orders of magnitudes slower. So it may not be worth to spend so much time for running a full benchmark suite, and maybe you want to even do a design space exploration, have different design combinations or multiple IPs to benchmark and so on. So usually for pre-silicon benchmarking, you're doing some modifications to reduce the turnaround time for example, efficient design space exploration. And typical things which we do for pre-silicon benchmark execution is to run only a subset of benchmarks. So in SpecIn, for example, or any other, just select those which are most relevant for your use case. Or the number of runs can be reduced. So rather than running each benchmark X times, just run them a tenth of those, or just a single time, or maybe twice to have like a warm-up run and then a single full run. So to reduce the number of runs. Also, there are some benchmarks which just run for a defined time and measure how many loop iterations, for example, they were able to execute during a specified time. Also, that is possible, but it basically results in a reduced number of runs for a benchmark. Eventually, you want to reduce the size of the workload. So in image processing or neural network processing, you can usually easily scale the input size. So rather than maybe running your network with a full 8 megapixel input, maybe you can run it with a 2 megapixel input, but you know that the runtime scales linearly with the resolution. So if you have such a priori knowledge about the scaling behavior of your KPIs for input parameters like input resolution, you may reduce the resolution for all the runs and do maybe one reference run at the full resolution and then scale those numbers to the respective range. And also, obviously, we can limit benchmarking to only the actual execution time or steady state. So if we recall the depiction of our software stack, we may not need to do a highest accurate benchmarking of the boot up process if we're only interested in the runtime of a, say, single frame of processing of our ADAS algorithm. So there is different mechanisms we can provide, and EDA vendors have implemented, or for example, we can even do a change in the fidelity of our DUT during runtime. So maybe you want to do a fast boot and then continue onwards in an accurate but much slower measurement of the actual benchmark. So that is possible. Or you may do a single boot once, checkpoint that, and only resume execution after that. So all of these are things very common in pre-silicon benchmark to have a reasonable turnaround time. With this, we will come to the second element of our benchmarking journey, which is the design under test. We try to draw a design space here for different implementation models and the main characteristics. So on the axis, you can see the simulation speed ratio related to physical reference. So on the very right, we see a 1 with high-level models or native acceleration being closer, sometimes eventually even slightly faster than executing this on physical silicon. And what these models mean, we will see on the next slide. But you see on the ordinate that this obviously has a trade-off in simulation accuracy, which could be timing, power, area. So every metric in our PPA, it will have an impact. So even though high-level models or native acceleration may be very fast, usually they are least accurate. But we can increase the accuracy going to System C kind of virtual models, or even RTL emulation and simulation. You see, if you choose RTL simulation or emulation, should not have an impact on the accuracy that you get from your results, but only on the simulation speed ratio, where simulation is much slower, but not depending on additional emulation hardware to run it. But emulation hardware is much faster. The highest accurate simulation we can do is even a gate level simulation, go to a physics kind of level. But this is, to be honest, not a very common case for the automotive benchmarks I have seen. We just listed it here for completeness or for some specific KPIs. If you need highest accurate power, for example, and you really want to have the high fidelity model there. But otherwise, usually you're fine with going between RTL and the high-level models. So what does this even mean? I will first describe the environments here on the left side, which we saw earlier. So the first column, before coming to the different accuracies we can see for and different other specifications or capabilities of each model. So silicon is our golden reference, right? The whole goal of pre-silicon benchmarking is to basically measure the KPIs as we would do on silicon, but just much earlier before it got manufactured, or maybe even before the design was frozen. So silicon is always our golden reference here in terms of timing accuracy, power accuracy, area accuracy, all of this. And the typical execution speed for this environment is about a gigahertz. CPUs may be faster, NPUs may be slower or in that range, but roughly a gigahertz that we see for time. Debugging capabilities is between kind of Ethernet UART debug on software level down to JTAG. So we have some ability to read out values, but not every signal, but only those from the JTAG chain. And the accuracy from execution is like the functional accuracy is really being bit accurate, or it's the golden reference for everything else. The fastest model we saw on the slide before is our high-level simulation model. Could be System C, could be instruction set simulators, could even be maybe native acceleration, as we see a latest push from ARM. Those are like one order of magnitude slower, so we're talking hundreds of megahertz, 100 megahertz up to a gigahertz. But the timing accuracy usually is untimed, too loosely timed. So there may be some timing annotation. There may be environments where you can replicate pipeline behaviors and so on to get some level of accuracy. We have had customers reporting that this accuracy on timing was not very appealing in the end, sometimes, but definitely it's an environment which has its purpose. You can do some level of power estimation. For example, you could get an instruction trace and then have a table of mapping instructions to energy consumption, for example, and thereby getting your power. That may be possible on some level of abstraction. The debugging capabilities usually are limited to software debug only, so even less than the silicon. But usually these environments are a bit accurate for all the register memory contents and so on. So maybe not for all signals internally, but for everything which you see from the programmer perspective. So these are definitely environments which have their absolute purpose in functional verification and all of this. And we can use them for some limited design space exploration as well for the PPA benchmark. The next three basically cover all the input format of RTL, which is the register transfer level. So this is basically the hardware description language, which is also used to manufacture a device. The capabilities do not, or more or less identical, but the different RTL execution environments define the achievable wall clock speed. So typically we have the fastest RTL execution pre-silicon on FPGAs. To give you a ballpark number, it's 5 to 50 megahertz, maybe depending on the design size. Certainly the larger the design, the more FPGAs need to be coupled together, the higher the latency and the slower the overall environment may get, but this is a rough estimation here. Emulators, usually specific dedicated emulation hardware, usually is slower, but also comes with additional features, which is mainly for estimation. So we can get pretty accurate traces of signals and use those for pretty accurate power estimation. That's definitely limited on FPGAs for the limited amount of resources we have. And also we have cycle accurate models for memory and so on. Similarly, we have for simulation. Only on FPGAs, if we use the native memories on the device, we may have cycle accuracy for everything that is an RTL on the device, but not necessarily for the memory hierarchy, if that is different to the memory devices, like maybe your FPGA uses an LPDDR4, but you're planning to use LPDDR5. So all of these could be differences in the timing accuracy. The large advantage of RTL is it is cycle accurate, definitely for the compute part, and in emulation and simulation case, even for the whole memory hierarchy and so on. Power is pretty accurate from activity traces of signals, which can even be kind of related to physical data. And also the debugging capabilities are very high, so we can see each and every signal if we need to. And of course, they are all fully bit accurate, including signals. Gate level simulation listed here for completeness is insanely slow, so we're talking less than kilohertz. Timing accuracy is much higher, like higher than cycle accuracy, which may not be needed in most cases unless you have a asynchronous circuit or something. But you get most accurate power measurements, including physics simulation. Yeah, you may see even gate level issues or other things which you can't see in RTL. And of course, they are fully bit accurate, including even voltage levels and so on. So we also wanted to list a few references here for these environments. For the high-level models, for example, for NPU, there is usually architecture-specific performance prediction models. Sometimes they do not even necessarily provide a functional output, but only focus on modeling the internal performance of that IP. For virtual models, we listed a few here. For CPUs, for example, QEMU is a very popular open source environment for executing instructions on a QEMU instruction set simulator. ARM is providing fast models of their devices, CPUs, and other IPs as well. There's instruction set simulators, others like for RISC-V IPs or RISC-V instruction set in general. There are system performance simulators like Gen5, which also include instruction set simulators or integrate those listed above, but then integrate also performance models of different cache hierarchies or so on. And then there is native acceleration, such as ARM on ARM. For the RTL case, there is EDA vendors providing the simulation, emulation, and FPGA environments. If you choose simulation or emulation, should not influence the KPIs as listed in the table earlier. In most cases, just a remark that the smaller your design, typically the faster it can run, especially if it fits on a single device, meaning a single FPGA or a single emulation core. Scaling across multiple chips is then always useful when you need larger capacity. For RTL and others, cycle-accurate IP execution does not guarantee cycle-accurate system performance benchmarks when memory interconnect or other elements are not modeled with equal timing accuracy. So there we always have to make sure that these timing accuracy kind of match to each other, that we actually get the system performance, which we are interested in most cases. And RTL simulation emulation may abstract different performance aspects. For example, dynamic voltage and frequency scaling, DVFS, is usually not modeled in RTL in the most cases that I have seen. But of course, there's an option to model that as well. We were already talking about system performance, interconnect, memory, and so on. So there is different memory models which you may want to use. The simplest model, and probably the one everybody starts usually with, is a fixed latency model. So there's different ways to implement it, but many models I have seen are just the number of cycles for read or write. Maybe you want to have different latencies for random accesses or subsequent accesses, like bursts, to where you access a memory range in a ordered manner, something like that. But it's pretty simple fixed latency model. You can even increase the accuracy of your measurement here by implementing the real DDR controller, having a model of a real LPDDR memory. So that could then model a complex memory system, even address slicing or other things. System level caches can be included and so on. So the modeling effort is higher, but also the accuracy that you can get is higher. We want to give you a guideline of where you typically get what. So this is the unordered list of people who may be involved in a pre-silicon benchmark. So tier 2s or semi companies They may provide system architecture, IP configurations, base software stacks, demonstration applications, system hardware software co-design. All of this could come from them. IP providers may be needed to provide the real IP, like RTL, virtual models, high-level models, whatever is available, but a model of the IP and IP-level hardware software co-design. EDA companies provide tooling, emulation hardware, services around that, all of this. So for Siemens EDAs, we don't have IP running those IP benchmarks. Competitive is a very decent business for us. So we even do full benchmarking services. Foundries may be needed to provide process design kits if we want to do area synthesis later on, or if we really want to go to a gate level simulation. Software companies may be needed for a commercial software stack, for benchmarks, for algorithms, and so on. And then last but not least, typically the ones requesting those benchmarks, OEMs and tier ones, they may have access to the end users, final customers, full system integrators, and so on. So they can give the system context here. With that, we want to give an overview of some exemplary DUT configurations. On the left-hand side, you see a colored block diagram of a typical system on chip. It has a CPU on the top left, a memory right next to it, and an NPU. Those are on top of a network on chip, which is basically connecting all these different IP blocks together and also connecting to the DRAM controllers on the right-hand side. And there may be other elements on an SoC, on a physical silicon, like a GPU, memory, real-time processors, peripherals, all of this. But in this case, this should be an exemplary DUT configuration for an NPU IP benchmarking. And for that, only those blocks, at least partially colored in blue, are actually modeled. So darker blue here means a high fidelity model, which could, for example, be RTL. The gradient boxes may have mixed fidelity, and then low fidelity boxes are just white. And you see a few errors depicted there. So basically in the guidelines, you will find the methodology to build your DUT configuration. In this case, first, an analysis of the performance defining relevant data paths is needed. This analysis was done. You can see a light arrow between CPU and NPU. This should visualize the communication where a CPU is starting to offload a neural network inference to the NPU. So basically just a trigger or a command, which neural network to execute from where. But afterwards, the CPU may not be heavily involved in the computation at all, but the NPU may be reading and writing data directly from local memory, from DRAM controllers, and so on. So there is different arrows to do a caching from DRAM into memory. NPU may read from those memory caches or directly from DRAM. So there is many reads and writes going on for the actual processing before the results are stored, and the CPU is just signaled that the computation is finished. So in this case, a high fidelity model of memory and NPU and network on chip are required. The DRAM you may model with a mixed fidelity, and the CPU may only be needed to have the appropriate hardware interface, have the communication and so on, and maybe some timing accuracy. But you could also get your performance numbers, for example, from signal traces down there without even respecting the software counters, if you used an untimed CPU model here together with highly accurate RTL or cycle accurate RTL for the other elements. In the second example, we're describing a freedom from interference use case. Also, that is some kind of pre-silicon benchmarking when there is interest in assessing freedom from interference capabilities. So, for example, there is a GPU in the system, and that GPU may be used for different purposes like ADAS and IVI. And you want to assess if the safety critical workloads are still prioritized and can achieve their safety targets or execution targets and so on. Then you just model, for example, the GPU and memory and network on chip. And all the other elements still need to be represented in some way. So earlier we have had NPU and peripherals here and so on. So those we may abstract with just load generators. And those generate additional traffic, which is representative of the system workload. And then we can run our freedom from interference analysis. With that, we're closing already the chapter of design under test implementation. Last element of our benchmark always is the KPI section. We already had in the introduction seen that it's mostly about performance, power, and area, PPA. So we list in our technical report many different KPIs for each of these categories. For performance, for example, there is a algorithm latency, for example, say in milliseconds. You may want to get a throughput, which is just normalizing the for example, in frames per second you can achieve, or pixels per second, the throughputs, operations per second, and so on. You may be interested in communication latency and throughput, for example, in a gigabit per second or any other unit. Sometimes, usually not only a single measurement is of interest, but also statistics. How does a latency vary between different system circumstances? For example, different load scenarios you may want to do in a pre-silicon benchmark, including worst case scenarios. The influence of elements of latency, for example, the interconnect or stack up of latency contributions. So to see really what's the impact of one of these elements on latency. You may want to see utilization. So usually the idea is to drive the utilization to say 80% or something, that you have some headroom, but don't waste your money on too much performance. So you may want to get a utilization percentage or a theoretical peak, something like that. Maximum clock frequency of the design may be a design target. So typically given in megahertz, gigahertz, something like that as a unit. Context switching performance, pipeline clearing, something like that, for example, can be read from performance monitoring units, PMUs. Cache hit miss rates, the percent of how much data was in which cache hierarchy, and so on. So all of this typically is monitored in the performance monitoring units. PMUs also be read out in the pre-silicon runtime. Freedom from interference analysis, quality of service analysis, real-time analysis, so application-specific real-time requirements that may be defined. And in many cases, the performance headroom for potential future updates needs to be respected, so utilization may not be 100%, but towards that. On the second P in our PPA on power, we have approximated power, for example, just looking at the toggling rate of a signal, which you may want to get in percent, or derived approximate power consumption in milliwatts. You can even get accurate power, for example, doing a cell synthesis, which would then require manufacturing process technology and bias voltage and so on, but you would get a more accurate milliwatts number. You may be interested in energy, given in millijoule or something, which includes both power and time. And that can even be normed to performance. So very common metrics are inferences per joule, FPS per watt, typical normations here. It's important to report the power mode if there is different available. And the peak clock frequency versus the sustainable mode was, or which clock frequency had been used during the pre-silicon benchmark. Potentially the specific operating point needs to be reported. For example, a specific clock frequency or signal toggling rate if that was achieved during the pre-silicon benchmark. Then it's important to know that it's much easier to do relative comparisons using the same tool, for example, comparing different IPs or comparing even a single IP in different design configurations rather than having absolute numbers, which may have their own inaccuracies. Then it's important to highlight what is included in the power measurements. Is it just the IP level power? Is it including the system level cache? Is it including memory? And so on. Exemplary use cases to fit the maximum performance into a given power budget. Also, that may be a valid pre-silicon benchmark. From power, typically you can derive thermal simulations. You may even see how your layout is heating up. So you would see something in degrees Celsius or Kelvin. Dynamic power versus static power ratios. So leakage could be reported explicitly, something like that. On area, there's mainly two things we can do. The first is just to run a synthesis to something. Even a DSP or an FPGA or an emulator may give you some level of information how large a design is, if it's mapping to some kind of registers, lookup table of different sizes, something like that. You can definitely do a relative comparison of designs. But of course, if you're interested in the cost for a tape out or something more precise than a technology node specific silicon area measurement, so synthesizing with a PDK, that is then giving you the square millimeter number you may be looking for. But keep in mind also there, of course, the more time you spend on optimizing the layout and so on, the more closer your numbers would be to physical silicon. So in many cases, relative size comparison is sufficient, and it just needs to be reported which IP elements are captured in the area. Finally, we include a table for the KPIs to DUT realization mapping here. So you see on the left-hand side in the first column, basically the first row is depicting the timing performance KPIs. The second row is for power KPIs, and third is for area KPIs. If we start from the left, if we just have a block diagram of architecture or datasheet, maybe we can do some extrapolation on performance KPIs from the theoretical peak or something. Maybe there is some level of extrapolation for power from peak or typical power, and some extrapolation from the tech node, but everything is not even like a rule of thumbs accuracy. For virtual models, there is model-dependent performance accuracy. We may get a first approximation for power, like instruction or transaction-based. And in many cases, not any area measurements at all, or it's very rough. Say we know how many max or something are fitted. In RTL, we have a cycle-accurate timing measurements, as depicted earlier. We can get activity-based power estimation, so high accuracy for power predictions, and you would get a approximation if you synthesize to something, or a gate count equivalent when you synthesize with the PDK and so on, which is then the last row, increasing area accuracy by doing a full synthesis basically. So square millimeter accurate area estimation, including layout. On the power side, you may even get layout aware power estimation, so highest accuracy, and your timing performance can even be sub-cycle accurate. Coming to future directions, we see the runtime of these benchmarks is increasing a lot. So there's more workloads, more configuration options for IPs, more complex workloads on the automotive side. So there is always research or development going on in reducing the simulation time for a benchmark by, for example, only model the required system, so reduce the system size, reduce workloads in a way we discussed earlier, but maybe there is also new ideas in the future. A big topic is access to platforms, especially in automotive. Not every OEM has an emulator or something in his basement. We offer something which you can basically get as a service and don't have to purchase it. I think every EDA company is offering something similar, but there's always improvements in how we can get access to these platforms. And it's not only the hardware side, but also creating these platforms is a huge services effort, not only involving technical, but also lengthy legal discussions. So there we are working on how can we make it easier for OEMs to do these benchmarks. How can we increase the collaboration between IP companies, EDA, OEMs, Tier 2s, and so on. The design complexity increases, and with that, the capacity that is needed on your FPGA or emulator or even simulator. So we're looking for other things like many-core, native acceleration, stuff like that. But of course, yeah, emulation capacity is always increasing. Yeah, emulation as a service we already discussed. Chiplets is a big topic, so we are looking into ways to encapsulating for a simplified exchange of real or full chiplet models. So on which level would we like to model UCIe to maybe have a system simulation even with one chiplet modeled in a way which you can just get and then fit your chiplet into that to have a system simulation, system and package simulation. And there is also additional use cases now popping up for package co-design. That you may want to get more accurate power traces or even derive thermals from that to see how your package substrate and so on may need to be designed. Release benchmarks may not yet use all APIs or the newest APIs, for example, Vulkan benchmarks or specific hardware unit benchmarks. So there's always improvements on the benchmark creation itself as well. Coming to the last chapter and also wrapping up this webinar, in the technical report, you find an RFI template. In this case, we did it exemplarily for an NPU benchmarking example. So in the report structure, for example, you find it should include a use case description, which in this case is a pre-silicon PPA benchmarking for a fixed NPU configuration with customer-provided workloads. Next, the hardware architecture and data path analysis should be depicted. So a block diagram, which we discussed earlier, I just copied it here in smaller scale. List of data paths and transactions, maybe with respective approximated bandwidth, split in read and write. So the input may be available system memory bandwidth or other system boundary conditions. All of this should be reported in your RFI report. Next is hardware configuration, so list of hardware elements, the IPs in the design, IP configuration, clock frequency, and so on. So there is an exemplary configuration which uses a small ARM Cortex-A55 modeled with ARM fast models combined with an NVIDIA deep learning accelerator, which is actually an open source NPU in RTL. In the large configuration, so AFM virtual model for CPU, RTL for the NPU. We may have an interconnect, some memory with some simplified latency model for on-chip, and then off-chip you also use a simplified latency model. The software stack should be reported in the RFI template. So in this case, for example, we used a very, very tiny Linux distribution of build root with a Linux kernel version, software stack, whatever had been executed, and so on. In this case, we say we executed the ML Commons MLPerf Inference Automotive, first release version 0.5 with SSD ResNet, resolution and so on need to be reported, and everything else which is requested from that benchmark. And then the report would include your performance KPIs as defined by the benchmark, so runtime of inference, optionally scale this to configuration, for example, inferences per megahertz, hardware utilization, visualized over a timeline, for example, or execution unit, the power and energy report, so a simple report with total power, total energy, a detailed report, which may even include leakage, dynamic power, and so on, performance normed to power, like picojoule per bit, something like that. And lastly, an area report, which may have implementation trial results in square millimeters, maybe even after place and route. So there should be more details how this was derived, and many more details can be found in the technical report. And as an input here, for example, the requester should specify which PDK, which tech node, is it a 5, 7, or 16 nanometer node, which should be used for synthesis. With this, I'm coming to a conclusion of this webinar, just in time after this 1 hour. We reviewed the table of the full content of the white paper. I recommend everybody to download it for free from the AVCC webpage. I highly appreciate your attendance and interest in this webinar. I was not seeing any question in the chat so far, and we have just reached the top of the hour of this webinar. So with that, thanks a lot, everybody, for attending, and I hope your next pre-silicon benchmark succeeds first time right. Goodbye.
Thank you, Nicolai. Everyone else, if you think of questions after the webinar, feel free to email them to info@avcc.org. And the link to download the paper is also in the chat function. Thank you, everyone, so much for attending.
Thanks a lot, everybody. Have a nice day. Goodbye.
Bye.